Well, essentially everything we've heard about the last couple of days, every major geophysical process, virtually everyone, involves either changes in the distribution of heat or heat flow discontinuities. So I think it's at least arguable that that knowing the thermal history of a rock or the thermal history of the planet is really tantamount to understanding its geological evolution. The idea, the concept of being able to use the inability of common or ubiquitous minerals to retain their radiogenic daughter product and take that information and turn it into quantitative temperature time histories is incredibly appealing. So too was an email I just got from the widow of a Nigerian dictator offering me to hold $4 million in trust for a very generous finder's fee. And I say this, or I make this comment because to some degree thermochronology is, and I haven't decided, is it in a midlife crisis or did it never achieve adulthood? You help me decide. But the good news, I guess, for the young folk in the audience, is that it isn't in sedate middle age. So actually, there's lots of opportunity for development, particularly defining kinetic calibrations, things like that. So there's a kind of a caveat emptor element that's going to accompany this talk, and this cartoon really sums up the point I want to drive home next hour and a half or 2 hours, however. That doesn't get a laugh. I could see we've tortured you too much. Okay, here's a cut to the cartoon thermal history. Imagine that this is a sample from a granitoid. It's been placed here, and it cools, magmatic heat being lost. It finds itself in the footwall of a normal fault, and it cools rapidly as the block is uplifted toward the surface of the Earth. The fault terminates here, and then it cools slowly as a result of denudation at the surface, bringing the sample closer to the Earth's surface. How best to get the information? How do we want to winnow that information out? And I'm going to return to this in a few moments, but first we'll get through the arithmetic. What is thermochronology? Thermochronology is essentially the diffusion equation plus, okay? I'm going to keep this relatively simple. Essentially, if you have ingrown radiogenic daughter product as a result of decay of whatever, uranium-238, potassium-40, rubidium-87. There's now a signature, there's a distinctive isotopic substance in your mineral that you can use to evaluate the temperature history. Take the simplest case, where we're only considering the diffusion loss, here's the diffusion coefficient, of this radiogenic daughter that's been grown into your mineral. You can solve the diffusion equation for a bunch of different geometries you see here. So imagine we have a mineral that seems like a plane sheet. It seems like something would be approximated by the blackboard here. And it lost 50% of its accumulated daughter product. It thought it was 1 billion years old. It got heated yesterday for a day, and it's now 500 million years old. Okay, so we've lost 50% of the daughter product. So the combined parameter, the diffusion coefficient, times the duration of heating, T, over the effective diffusion length scale squared, note that this is dimensionless, has a value of 0.2. Okay, we can measure R. I just told you that T, the time scale, was a day. So in fact, we can solve for D. We have value for the diffusion coefficient. Now, if the rate limiting transport step is diffusion and it obeys an Arrhenius relationship, which Greg has been good enough to describe to you in the previous lecture, where this is the pre-exponential, this is the frequency factor, this is the activation energy, which in fact is essentially the sum of both the defect formation, vacancy formation, and migration of the diffusing species. R is the gas constant and T is absolute temperature. And once we make this step, we can then translate D, if we know E and D naught, we can translate that value of the diffusion coefficient into temperature. It's the only thing we don't know. Now, let's say that I didn't know that the heating duration was 1 day. Let's say that that's an unknown. It turns out even if I don't know it to a factor of 2 or 5 or maybe even 10, the temperature dependence is typically so great that it really won't unduly affect my estimate of peak temperature. For example, before I came to UCLA, I was upstate New York in SUNY Albany, and I made the point that if, let's say in the coldest winter night in Albany, gets down to minus 30 Celsius, I'm walking out to the woodshed, and I'm doing 2 miles an hour, puttering out there. I want to get back to the house. If I had the same temperature dependence as an argon atom does in a potassium feldspar, about 46 kilocalories per mole, then on the hottest summer day, 40 plus Celsius, I would be going 10 billion miles an hour. Okay, that's fast. And that's over 70 degrees, 10 orders of magnitude change in rate constant. So, I could be wrong in my guess of time scale of this heating event, by a considerable amount and not really substantially affect. So this is the single biggest plus for thermochronology, is this extremely strong temperature dependence. Okay, but actually this is kind of uninteresting in the sense that it's a static problem. You generate some daughter product in a mineral, you expose it to an episode, a moment in time, and it experiences some exchange, you calculate the temperature. But more interesting is the case where actually the daughter product is leaking out in real time. We have ingrowth simultaneous with loss. Okay? And lastly, to point out that although this equation appears to be for a constant diffusion coefficient, provided that the diffusion loss is characterized by the Arrhenius relationship, in fact, you can make this transformation that, in fact, D can be a function. It doesn't have to be constant. It can be any any complex function of temperature time, and any solution to the diffusion equation is valid. Okay? So when you add all these things up, you come up with this diffusion, accumulation, cooling equation, which is what, with the various parameters, you can read this faster than I can relate them, which is, in fact, the equation, this accumulation, diffusion loss, that Martin Dodson solved in his classic 1973 paper to yield what I'm calling the bulk closure temperature equation. Okay? And let's have a look at it here. This is the activation energy. We've spoken about that, the gas constant. Here's the closure temperature, and it's a function of a geometric constant. Spheres or cylinders or whatever arbitrary geometry you want are going to retain the daughter product to different degrees, different surface to volume ratios. This is a time constant that tells the equation how quickly the diffusion coefficient is changing with temperature. For example, if you're cooling linear and 1 over temperature, how quickly the diffusion coefficient, in fact, is increasing with time. Again, here's the characteristic diffusion length scale squared, activation energy gain, and the cooling rate. And Dodson, actually, this equation appeared in the abstract of his paper. This is now, almost 40 years ago. And because we were, because of the times, he didn't actually think to publish this. Actually, he didn't actually formally evaluate the real equation. This is simply an approximation of a special case of what he did present, which was the full equation for the closure temperature as a function of spatial position in a solid. So what he presented was essentially the average closure temperature of a system. And how does it work? Well, imagine now here's temperature, here's time progressing to the right. And at high temperature, daughter products for the most part aren't going to be happy in the lattice that they've abruptly appeared in. For example, any beta decay, you're going to start in one column of the periodic table and you're going to move to the left or the right. Okay, so for example, potassium 40 in column 1, either you go to argon, which is an inert gas, or you transmute to calcium. So you go from an alkaline metal to an alkaline earth, different valence. They're typically not going to be happy. For example, the solubility of argon in a mineral partitioned between a vapor phase and the solid is infinitely high in the vapor phase. So it's not real happy. So it's going to tend to want to migrate out. So at high temperature, the daughter to parent ratio, let's say in this case argon to potassium, is 0 because we're leaking the daughter product as soon as it gets produced. Eventually, temperature drops to the point where, given the kinetics, the argon starts to be, a little happier on longer time scales. It's starting to hang around. But there's a transition through which there's partial retentivity until the temperature drops to a point where, for all intents and purposes, that daughter product's fixed. And remember, temperature range isn't going to be that great because of this extremely strong temperature dependence. Remember the 10 billion miles an hour. So essentially, the bulk closure temperature is the extrapolation of this linear segment here, daughter to parent growing, well, not broadly linear in time. It's going to be curved because, of course, the parent concentration is decreasing as a result of the decay. But it's the extrapolation of this curve back to the time axis, and that corresponds to something that we're going to call the closure temperature. Okay, now that was sort of necessarily where we started. But the real potential of the method, and something that I'm going to emphasize is underexploited, is this, which is the actual formal closure equation. This is the closure temperature. It's a function of a bunch of, here's a constant, tau again, frequency factor, and this term here, which is geometry dependent. But what this is saying is that the closure temperature is a function of spatial position. If you're in the center of an object, a solid like this, you have a greater retentivity. You're farther away from a diffusion boundary than you would be if you started life right here. In fact, you start right here, you got a 50% chance of, in fact, diffusing right out in the first first diffusion hop. So this is the continuous closure equation. We're going to be able to, if we could, reveal within solids the distribution in situ of the daughter product following some thermal history, some closure interval. Then we're going to be able to get a continuous temperature time history. Now let's come back to our example. Here's the history I mentioned, and in terms of mountain building, right? Well, these are bits of information we want to know. We want to know when the magmatic inflation period of the range was. We want to know what the style of cooling was. It hydrothermally assisted or was it conductive? We want to know the history of faults that involve ramps, because thrust, depending on whether you're hanging on a footwall, a thrust, or a normal fault, is going to either heat or cool you. And if we, in fact, can constrain the time at which this hypothetical normal fault began, and of course the rate of cooling, if it cools like this, the slip rate on the normal fault is less than if it cools like this or if it cools like that. Okay, and then we want to learn about the surface denudation because we can say something potentially about landscape evolution and the like. The downside is if we use the bulk closure equation, we have a variety of strategies we can use. The Argon 4039 system I'm going to talk about a fair bit. We can look at accessory minerals using thermal ionization mass spectrometry. And what we get is essentially a datum, a temperature, okay, a closure temperature, and associated with a bulk age. The downside, as you see here, is we have 3 hypothetical thermochronometers, and the temptation is going to be to draw a straight line through them. And what we have in fact have lost the fundamentally interesting information in that system. If, however, we can recover the internal isotope distribution, the daughter product, then either, in fact, inferring it by method we're going to talk a fair bit about, Argon 4039, or actually directly measuring it using secondary ion mass spectrometry. I'm going to briefly touch on this. This is sort of more in the developmental stage. We can recover with some objective measure of uncertainty the accurate and precise continuous thermal history from which we can then make much clearer statements about the mountain building process than if we were joining the dots. Okay, not to give Greg a hard time here, but he sort of set me up the way I did with his pseudo-tacholite question. with his thermochronological example. I'm going to give you an example of, let's say that this thermochronometer here is biotite, and it is certainly, if you Google, biotite closure temperature, you get, a gazillion more hits than you would if it were potassium feldspar, say. The good news is that biotite phlogopite are in this solid solution. Relatively speaking, it's extremely well characterized. We have measurements at the phlogopite end member and 2 intermediate values of iron to magnesium ratio. In fact, here's one case. This is from Harrison et al. 85. So the diffusion coefficient as a function of temperature is pretty well characterized. But as a result of these studies, we've discovered that the closure temperature, in fact, can vary substantially. This is kind of the classic, this comes off the web. I think this originated in Stanford, and this is sort of the, again, kind of a cartoon view of thermochronology, which is you have a mineral, a fission track zircon dating, for example, and the closure temperature is 200 to 250 degrees, something like that. Well, it's hard to go to the literature and find the experimental calibration that what essentially happens is somebody propagates a rumor in the literature that says the closure temperature of biotite is 300 plus or minus 50 degrees. And despite the fact that we now know that the closure temperature of biotite can vary, certainly because the effective diffusion radius in published studies varies by a factor of at least 6, by directly measuring in the laboratory the effective iron-magnesium ratio, we find, you can see closure temperature variations of over 50 degrees. The nature of aluminum occupancy, it changes closure temperature by tens of degrees. The halogen content is an extremely significant. You can change the closure temperature 100 degrees depending on how much OH or fluorine and chlorine. And of course, they're all a function of cooling rate and pressure. My point is that actually there are biotites that have a closure temperature of 350 degrees. But subtle changes in the halogen content or the aluminum occupancy or the iron-magnesium ratio, it can make it 450. And indeed, the range of closure temperatures is, substantial, much greater than you would guess by looking at the literature and seeing these nominal closure temperatures. So, and actually, interestingly, I pointed out to Greg at the break that this range of 300 degrees was exactly the bound between his upper and lower curve in that figure he showed. So it doesn't change your argument at all. But the implied precision or knowledge of any arbitrary mineral having this characteristic is illusory. Okay, let's get started here on the potassium, calcium, argon 40 decay system. Potassium 40, as a parent, it has decays to both. Calcium 40, in fact, notice that nearly 90% of all decays go to calcium 40. About 10% of the other 10%, by a variety of mechanisms, go to argon 40. And despite this being the minority partner, this is the one that you've heard about before because silicates don't like to make compounds with rare gases. So initially most silicates will have very low concentrations of the daughter product. Notice that actually a minor branch, but nonetheless significant, is this positron emission to argon 40. So as you cuddle tonight with your partner, note that in fact you are irradiating that person with antimatter at a relatively low level, but in the course of one evening there will be antimatter exchanged. Okay. So this potassium argon dating, or the 4039 variant I'll get to in a sec, this is routine, despite being, as I say, the only 10% of the decays. What's the problem? Well, calcium 40, in fact, is about 1.5% of the entire mass of the planet. So there's calcium. We're rotten with calcium 40. Seeing a radiogenic contribution to calcium 40 in most Earth materials is going to be difficult. Potassium 40, in fact, is only 20 parts per billion. So in fact, there isn't a whole lot of parent relative to this. We're living in this sea of calcium-40. So really, the reason you haven't heard of this technique before probably is it's really restricted to very old high potassium calcium phases. But in fact, it's making a comeback for reasons you'll see in a bit. Okay, argon's an inert gas. In fact, it's going to be perfect for our purposes, right? It's going to be able to migrate. We're not going to have to accommodate any kind of electronic charge balance during its migration. It's an inert gas. It doesn't want to be in the silicate. So surely this is the perfect case of a daughter product that simply originates in a silicate lattice and is in fact looking to get into the atmosphere because that's where it's going to be happiest. The 4039 variant of potassium argon dating is an important step. And I'll explain to the potassium 40, in fact, is in a constant isotopic abundance with potassium 39. This is the big guy. Again, as I mentioned, potassium 40 is 1/10,000th of potassium 39. So what we're going to do is we're going to irradiate. We're going to put our sample, our unknown, into a nuclear reactor. We're going to irradiate it with fast neutrons, produce this NP reaction that transmutes a small fraction of the potassium 39 into argon 39. Okay? So take the case like this cartoon here. Here's the center of our crystal. Here's the margin. And imagine that diffusion is the rate-limiting transport mechanism. It doesn't have to be. If I was in that one of Greg's shear zones, recrystallization is going to be the rate-limiting step for getting the argon out of that sample. You've got vacancies migrating in response to the strain rather than just thermally. So this is only going to work for us when the solid is not deforming. Okay, so we've got a uniform distribution of potassium. Let's say the mineral is biotite. Okay, so it's everywhere going to be around 8% potassium. So we're going to induce into this sample a uniform distribution of argon 40 after some time. Now we put it in the reactor where we irradiate. It's going to have a uniform distribution of argon 39. There's a little recoil over some fraction of a micron or so. But for the most part, the mineral is big relative to the recoil length. So we have this uniform distribution. Now we take that sample, we put it in a vacuum, a high vacuum, adjacent to our mass spectrometer, and we begin to cook the sample up. We heat the sample, and what's going to happen is we're going to diffuse radiogenic argon and this artifactual argon 39 to the surface. Okay, we can capture, we can put it into our mass spectrometer, and we can measure the argon 40-39 ratio, which is implicitly age, right? This is, in fact, the daughter to parent ratio because 39 is a proxy for potassium 40. Okay? So, in fact, because the argon 40 is uniformly distributed, we're going to get a uniform age or uniform plateau, it's referred to. And if, in fact, this is an undisturbed volcanic rock, we can be pretty happy in saying that's the age, 100 million years, that's the age that this volcanic rock was erupted and rapidly cooled. The more interesting case is where the sample has been held at temperature high enough that argon is unstable, it's diffusing out this boundary here, and we have this decay distribution as a result of natural loss. We put the argon 39 in, we step heat. The initial step, the initial infinitesimal degassing, in fact, has a infinite flux of the argon 39, right? That's concentration, there's a delta function right there, and a finite flux of 40, so the ratio and the age is 0. And that as we heat the sample up, we're going to be, in fact, probing regions more and more remote from the crystal surface, and the age is, in fact, going to rise, potentially as high as the original age of the sample, but depending if it's heavily degassed, maybe not. If some time elapses between this heating event and us measuring the sample, let's say there's a heating event 100 million years ago, then what we're going to see when we irradiate the sample is there'll be a uniform distribution from the last 100 million years and capped by this error function type profile up here. And we heat the sample, and what we're going to say is, look, this is the age we think that the sample got degassed, This is the age it was before, or at least the minimum estimate, and the amount of argon that's missing is proportional. The fractional loss is proportional to dt over a squared. Remember that joint parameter, that dimensionless parameter, the diffusion coefficient, the heating time over the diffusion length scale squared, and we're going to then be able to solve for the thermal history. So if the kinetics are known, we're going to be able to invert this to yield a continuous thermal history. A bunch of different formulations of thinking about daughter product transport in silicates. The multi-diffusion model we're going to focus on. I'm going to multi-path model. In fact, just frankly doesn't work. It fails in obvious ways. And then this is a straw man model set up, and I'm going to just briefly come back and talk about this. This is a very different idea. But let's first focus on the multi-diffusion domain model. And that is simply that it imagines that natural materials, that the likelihood of nature producing a biotite, say, in which every single crystal in that granite or that gneiss has the same diffusion length scale for argon is low. So here's a simplification. Let's imagine that this mineral contains some big domains. Say one third of the domains are big, another third are smaller, and the last third are really small. Okay. Let's just take that for what it's worth. Now, if we're going to try and extract thermal history information out of a solid using that formulation, there's a couple of things that that we absolutely have to adhere to. Okay. And the first is that because I'm not going to say that the closure temperature of biotite is 300 degrees. I'm going to let the sample tell me what its closure temperature is. I'm going to get a customized Arrhenius relationship as a byproduct of actually revealing the internal distribution of the daughter product. But this is the fundamental requirement. If argon diffusion in the lab, if I screw up, if I don't keep the mineral stable, or if I melt it, or if the diffusion mechanisms, Greg showed a plot of dislocation creep, versus with a thermal component, and you're going to what if the diffusion mechanisms that are important on timescales of 10 to the 7th years, in fact, are irrelevant in the laboratory scale, then I'm in trouble. So, but what I need then is that the way the argon comes out of our sample in the lab has to in fact be to high fidelity, mimic the argon loss in nature. That is the same diffusion mechanisms, the same diffusion domains, same boundaries. Okay? Yep?
Is the size of the sample that you're working with sort of based on the required amount of argon that you need to get your instrument sensitivity measured?
Yeah, that's true. It used to be that we had to shovel grams of sample into your crucible, and we're now down to where 3 milligrams is a lot because mass spectrometers are becoming more sensitive. But there's a risk there, and that is if this is my sample, right, and here are the diffusion domains in that sample, and I decide to crush my sample up to get uniform particles of this size, what will I have done? And that's a rhetorical question. I've learned from Greg's talk that you guys don't like the Socratic approach very much. So unless you ask who loves to answer questions, in which case the lack of hands is a clear acknowledgement that nobody does. Okay, so I'll answer my question. What's going to happen is where you would have seen a fairly retentive diffusion domain, you in fact have artificially made it unretentive. And I'm actually going to show you a couple of examples of that. That's the problem. So the temptation as we've gotten to the ability to measure vanishingly small amounts of material is that we're actually going to violate one of these criteria, which is it has to be the same diffusion domain and boundary that existed in nature. Experimental considerations. These are simply, I mentioned argon 39. It does recoil when you make that thing with a 2 MeV a neutron in the reactor, the likelihood is that the target isn't going to be in the same lattice position as it started, okay? But as long as your mineral domains are big relative to the recoil length this point is basically 50, 80 nanometers. So as long as your diffusion domain is at least a couple of tenths of a micron, you're okay. Must be stable, and yeah. And then there's other things, there's other requirements of the model that really are simply, we just didn't want to make the model any more complicated than it had to be. But anything that you read here, if the potassium isn't homogeneously distributed, then make a model in which the potassium is not uniformly distributed. It's okay. The diffusion domains assume not to interact. Remember this one, because all that is a requirement of the model. I'm going to come back and deal with this later, because there's a difference between having a physical model that actually describes what your sample is doing and a physical model that actually reproduces or recovers your thermal history information with high fidelity. Those are not necessarily the same thing. You can screw up. You can have a bad formulation that completely misses the fundamental nature of the sample. Okay? But as long as it assumes volume diffusion, you actually can't help but recover an accurate thermal history. Okay? And I'm going to demonstrate that to you in a bit. Okay, so here it is. I'm going to hit you hard. This is an Argon 4039A spectrum of a sample of a potassium feldspar from Tibet. We're going to come back to this guy in a little bit too. Here's the parent age. This is the Argon 4039 ratio. And notice that when we degassed it in the lab, it didn't yield a constant age of 100 million years. It started off down here. It was a little blurry. We actually have a correction. I'm going to show this to you in a bit. We can recover. There's some excess argon in here. So follow the yellow line and then the cyan. That's the age spectrum. Okay? And you notice that it actually has a kind of a sinuous form. It rises and then it comes and there's another sort of false summit. The same time that we're measuring the 4039 ratio and thus age, we're extracting information from the Argon 39 that we know was uniformly distributed. Remember, we made that yesterday in a nuclear reactor. We can calculate diffusion coefficients from a solution of the diffusion equation you saw earlier. We calculated the apparent Argon 39 diffusion coefficient over the domain scale squared versus reciprocal absolute temperature. And what we see are these yellow dots. And what we typically do is we analyze this. We heat the sample to 400 degrees and then 400 degrees, 450, 450, 500, 500, for reasons that will become clear. And you notice that the initial segment, this is almost true in almost all cases, is linear and yields an activation energy somewhere around 46 kilocalories per mole with some distribution. The more steps you get in here, the longer this linear array here, the closer you get to 46 kilocalories. But then it falls away. Okay, and it looks like the activation energy is getting shallower and shallower, and of course that's not what's happening, I'm sure. If we make a model and we say, look, imagine that this sample contains 1, 2, 3, 4, 5, 6 different domains. There's a big domain, there's a bunch of progressively smaller domains, and the thickness of the line is supposed to indicate some measure of the relative abundance. So this is this is less than 1% of the sample, and this would be close to 40% and so on. You can see that I can extract, or at least I can reproduce the Arrhenius data here very closely. That the model is in red. Okay, it doesn't mean it's right, but we can mimic it very closely. Eventually you get up to 1100 degrees. You get here, we keep heating the sample at 1100. We don't want to melt it, but eventually, NSF grants have a finite deadline. We can't wait 3 years to melt our sample, because getting the last gas out of in a diffusion, right? Initially, the concentration gradient is infinite, okay? And then as you degrade, it's going to take a long time to completely degas. So what we do is we take it up to above 1100 degrees, and you see that the relationship breaks down, as it should. We melted the sample, okay? Now, here's something Arrhenius plots have a problem with step heating data like this. What we prefer to do is define this initial linear segment. We're going to call this green line R0. It's going to be our standard. And then what we're going to do is we're going to look at the deviation between any diffusion datum and the extrapolation of that green line. So here's no deviation between the green line, between the sample and R naught. And here's a big deviation between the data. So if we plot, again, cumulative percent 39 released, beginning of the experiment, the end, you'll see that we, in fact, can nicely model the Arrhenius data on this plot. And it has the advantage that independent of thermal history in the lab, this doesn't change. If I double the time I'm heating in the lab, it'll completely change this plot, right? This thing here, because it's going to lose more argon, is going to plot up here. Okay. So now we've got everything we need to know. As a result of modeling the Arrhenius data with the 6 domains you showed here, I have information about what the frequency factor is. I've got the activation energy. I know what the relative size and relative volume fraction of these different size domains are from, I made that model myself. I can then take this Arrhenius data here, the age spectrum, and I can jointly invert it, and I get a continuous thermal history shown here. Okay? When in fact, the age gets high enough that we're starting to in fact lose radiogenic, the errors blow up. So really, what you want to do is you want to look at this age spectrum between about 32 and 9 million years. So between about here and here, we have our continuous thermal history. Now, I've made an assumption in recovering this thermal history, and that is cooling was monotonic. That is, this doesn't have to cool linear in 1 over T. It could, in fact, remain isothermal for a long period of time, but the temperature can never increase. So I've imposed on this, if I make that assumption, the monotonic assumption, then, in fact, these things can routinely be inverted to yield a unique thermal history. You might have noticed, your eye might have caught this, that the inflections in the age spectrum are similar to the inflections in the Arrhenius. These are 2 different bits of information. This is calculated from the release of Argon-39 that I made in the reactor last week. This reflects the distribution, the ingrowth of Argon-40 in the sample over tens of millions or maybe even hundreds of millions of years. I'm going to show you a few examples. Here's some models for, here's a sample I just showed you, NG13. Here's the age spectrum, and here's its, and your eye can see these inflections are correlated. This is important, right? Because these are independent variables. When I use the correlation theorem and I look at the rate of change as a function of cumulative percent 39 released, that sample I just showed you has a correlation coefficient of 0.99. And these other ones, they're different. Some are linear. This shows essentially a continuous distribution of domain sizes. This more discrete. You can get values as high as 0.99. Well, this is our prima facie evidence that the diffusion mechanisms and boundaries that were defined the argon retentivity in nature are the ones that we're interrogating in the laboratory. Otherwise, we wouldn't see. If, in fact, if I did, if I can purposefully crush my sample below the effective diffusion radius, and I can obliterate this correlation. I'll show you examples of that. So this is how we know that, at least in these cases, we're doing something right. Now, in fact, here's the N13 K feldspar. If I look at this correlation, okay, here's my model for the age spectrum. Here's my model for the R-naught product. If I correlate them directly, I get this high degree of correlation. What if I, in fact, I make a periodic function out of both of these and then start to shift them out of phase? It's fascinating. Okay, if I take the age spectrum, auto-correlate it with itself, of course, I get a correlation coefficient of 1. As I start to shift it out of phase, let's say by 5%, I've dropped the correlation to 0.7, and eventually it drops quickly to 1. But if I take the cross correlation between the age and the Arrhenius, the log R-naught spectrum, in fact, it behaves the same way. This, again, to me, is prima facie evidence that, at least in the case of these samples, the diffusion boundaries and the conservation of diffusion mechanism assumption is met. Okay, now life isn't all that pretty because you often see, this is classic of the Himalaya. In fact, I'm going to talk about the Himalaya Tibet to you guys on Thursday. I'm not going to show a lot of argon data because actually those samples, because of part of their geodynamic environment, contain lots of excess argon. I mentioned that the partition between argon molecule between a solid and a vapor is infinitely higher, and well, sometimes the argon pressures can be really high, and in fact, the reverse happens. Argon goes in. So here's a case of a granitoid from a 19 million year old Pluton in the South Tibetan detachment. So in fact, the oldest this thing could be is right here. We got ages as high as 150 million years, and in a sort of spasmodic. This is low temperature excess argon, high temperature excess argon. You're pretty much done. This is actually another phenomena that you see this intermediate age peak, and in simple diffusion theory, this is impossible. Okay, this isn't impossible, however, if I have a diffusion domain like this that has, radial concentration. I irradiate that, and then I break that domain and degas it. In the lab, it's possible to create these sorts of, or to break up the high degree of correlation. There's an extreme case here. Here's a case that has high temperature excess argon and low temperature excess argon. And notice this funny, periodic bouncing around of age. In fact, not only when we irradiate the sample, we're actually making all kinds of nuclear reactions when we hit this thing with fast neutrons. One of them actually is a reaction on chlorine that produces an argon isotope, produces argon-36, argon-38. And we can capture that. And I mentioned to you that argon-39 is a measure of potassium. So this is essentially, we can look at the chlorine-potassium ratio in our sample, step heat it, and you see this extraordinary correlation. That when you take your sample, you measure it at 400 degrees and 400 degrees. The first step is very old and has high chlorine potassium. The second step is younger and has low chlorine potassium. In fact, what we're seeing is excess argon actually trapped in saline fluid inclusions. And as you take your sample up to a new temperature, you blow that inclusion and you make another train of smaller inclusions that have higher decrepitation temperatures. But what's cool is if you take the difference between that age and that age, okay, that's delta argon 40 delta potassium, right? And the difference between that step, that's the difference between chlorine and potassium. In fact, it makes linear correlation, the slope of which is actually the excess argon to chlorine ratio. Okay? Now we plot delta chlorine potassium, the delta age. Okay? When we use that ratio, we can correct, because we know the chlorine potassium, okay, then it's simply, there's the chlorine potassium ratio of our step. There's the excess argon to chlorine ratio of that fluid. I'm just going to subtract that away, and this spasmodic looking H spectra becomes the one shown in red at about 100 million years. This is a 100 million year old Andean Pluton from southern Tibet. Okay, now not everything is apples. Here's we believe the canonical activation energy for K feldspar is 46 kilocalories per mole, and most data show that. But in fact, you get a real spread from about 30 to 60. Notice though, when you plot the amount of argon-39, how robust was that initial activation energy. So the more of the 39 release you have, the better you can better calibrate it, the better leverage you have on the slope. And you can see that there's a relation. Clearly, in samples in which there's a very small volume fraction of small domains, you can lose, you can really almost completely lose information about the activation energy. The fascinating thing is, if you plot activation energy versus frequency factor, you get this extraordinary high correlated diffusion compensation. That is between the frequency, log of the frequency factor, and the activation energy. So even though our technique, in fact, in many cases, for example, like down here and up here, isn't revealing to us the accurate, or what we think is the canonical activation energy, it actually doesn't matter. Because at the same time you change, if this is, well, I've got a good one here. Thanks. Yeah, this is log d on r squared, and this is 1 over t. And this is sort of the geological, temperature interval of interest. And these are our log r naught data. It really isn't going to matter too much extrapolating into this geological region here, whether we overestimate it or underestimate it. Because if we overestimate, we're going to compensate by getting a much higher frequency factor, and vice versa. Okay? So again, I mean, I'm not selling a 60 kilocalorie as being, geologically meaningful, but what I'm after is thermal history information, and what I'm saying is it doesn't really matter. Okay, we put together a big database some years ago, a couple hundred samples, and what we found is that a good sort of third of them had this low temperature excess argon, but that correction mechanism I showed you, the excess argon chlorine correction mechanism, actually allowed us to correct it. High temperature, you're done. Okay, high temperature excess argon, and that's kind of a problem with the Himalaya. This intermediate age maxima, something like a quarter of samples, but when you put them all together, here's a subset of the database. If you look at a cumulative fraction of samples that yield, as a function of the correlation coefficient, and actually I won't dwell on this, but what you want to do is look at the cyan line. You can see that about a third of the samples we measure have correlation coefficients below 0.9. And that's our criteria. If your Arrhenius data and your age spectra don't yield a correlation coefficient as high as 0.9, then move on. Don't bother doing a thermal history analysis, and certainly don't show up at AGU with a correlation coefficient of, where I'm going with this, right, of 0.5, and say the multi-domain method doesn't work. Okay? Because there's an operator effect. Okay, let's say the method itself, bottom, the proof is in the pudding. It's internally consistent when you look at a large database of these K feldspars. And it's also externally consistent, although there's a concern I have that, it took us a long time, a dozen years of fairly active, critiquing in the community before this really caught on. And now I worry that we've sort of become a gold standard. Okay, and I say that because here's that age spectra sample I think I showed you earlier. No, and I'll show you actually in the next slide. Here's the biotite. Now notice the biotites range over tens of millions of years here, and they've all been set at 350 degrees. But probably not, in this case, not because we know the FeMg ratio, or we know the aluminum occupancy, or we know the halogen, simply because this has been taken. Down here, the apatite fission track stuff, there's not only, here's the helium data, apatite. This is very well constrained in terms of it. I think, Dave, are you going to speak to this group sometime?
Possible.
Yeah. So, in fact, yeah, I'm not really talking about this, the uranium, thorium, helium, lower temperature stuff, because I think that understood Dave is. But now you see up here, there seems to be agreement between monazite uranium, thorium, helium, and the K feldspar zircon fission track. The zircon fission track, in fact, has been raised by about 50 degrees from that plot I showed you earlier. And in this case, I think we're starting to chase our tail. That folks are now starting to modify these nominal calculations based on the agreement with K feldspar, and really these things should be independently calibrated. Okay, this is actually the same sample. In terms of the inversion, they're pretty straightforward. I just show you this because here's a case where we did an interlaboratory comparison with Pete Zeitler at Lehigh. This is the same sample I just showed you. What we do is use a variational approach. You develop a polynomial that describes the age spectrum and the Arrhenius plot, and then essentially start with a random thermal history, and then randomly vary the position on the temperature time history. That either improves or it makes the fit crappier. If it improves it, basically you go in that direction and you run it until you get a minimization. And then you do this a lot of times, and so these plots I'm showing you are basically the 90% median and distribution of large numbers of these initially random thermal histories. Pete Zeitler uses something controlled random search method, more of a Monte Carlo approach, where he's not actually conditioning. He's not using the goodness of fit after every run to in fact direct it's essentially random. And I point out that here's the two different approaches, really essentially yielding the same thermal history. Now that's the case for monotonic cooling or monotonic thermal history. What about the more interesting case where the temperature can go up or the temperature can go down or it can stay constant? Really, I wouldn't say all bets are off, but you really lose substantial clarity in the thermal histories. Here's a feldspar I'm going to show you, but from in the next slide, NM1K feldspar. This is from Tibetan granitoid. I'll show you a set. Here's the monotonic thermal history, the 90% median shown here in yellow. When we release the monotonic constraint, okay, so now you could in fact have a thermal history that would wander all over the place. It could go up to 1200 degrees, and in fact the only solutions actually, although a little fuzzier, in fact here's a hot spot here, so in fact in either approach there's no way that you can avoid having been at that temperature at that time in this, at least in this calibration. In some cases it's not so good. Here's a case where in fact the non-monotonic seems to want to have cooled it down and then been at a higher temperature, and these are in part compensatory. Okay, so you can see in many cases the thermal history is such that really the only information you get is the last time the sample was at, say, 300 or 320 degrees, something like that. Okay, let's look at this guy. Actually, he comes from, this is kind of neat, and actually this is work that David and I are just embarking on. We're heading off to Tibet next year to follow up on this. This is a granitoid right adjacent to suture. Talk more about this on Thursday. The Yarla Zangbo suture. In fact, the suture runs right through here. There's a north dipping thrust fault, the Gangdesi thrust right through here. We've looked at samples in this vertical traverse between NM1 and 7, and I plot for you here the results of the multi-domain analysis. As you'd imagine, the sample here, NM1 at the top, does this make sense? Yeah, NM7, of course, that's right. It's at 24 million years. It's at the top. It's cooler than the one at the base. Oh, yeah. This was. We didn't actually collect a rock and then carry it up the hill. We started at 7 and went down. That distance, 300 meters, something like that. That's a kilometer. Yeah, no, we decided we're going to collect 7. We're going to have, similar vertical separation. Okay, so what's cool about this? Now, this is not a great example because the reason why this temperature over 1 kilometer is so big is that, in fact, this granitoid was emplaced at 30 million years. So we're actually seeing this is magmatic heat dissipating. But now imagine that this was, isotherms were horizontal. Having these vertical, the difference here, the decreasing distance, is telling you about the changing paleo geotherm. So it's possible to use a high fidelity method like this to actually see changes in the in geotherm through time using this vertical sampling strategy. Okay, coming back to the heterogeneous diffusion model. This is absurd. This is a model that, in fact, was proposed by critics about 15, 18 years ago, which was based on their sort of mineralogist conception of a feldspar, which is You've got big regions in a potassium feldspar of so-called tweed, blocky tweed, low dislocation, low defect, pure orthoclase, surrounded by so-called modified feldspar then perthitic, albite exolved perthites. And so the conception was that this is the core of your sample. You have very low diffusion in the big homogeneous blocky region, but in fact it was separated from the diffusion boundary by these regions of higher permeability, diffusion permeability materials. So imagine now, here's your crystal. The core has very relatively low diffusivity. Okay, then there's a kind of a bullet-shaped region with much higher, then a rim with somewhat lower but higher than the core, so like this. So this was a fanciful model, heuristic model, developed to drive a point home, which is if you took this model, what does the R&R knot plot look like? Well, this is the R&R knot plot. So say a very different conceptualization. The only thing it shares in common with the multi-domain model is that Arrhenius behavior in the diffusion migration. Okay, so what we did is we then forced this model through the multi-domain fit. So here's the parent age spectrum that came out of us degassing in the computer this sample, and here's the multi-domain fit. Looks real good, same nice fit to the Arrhenius data. And here's, in fact, the thermal history that results. Here's the actual thermal history that went into the box, into the computer. And here's what the computer said that thermal history would appear if we forced it through a different fundamentally formulated model. And you can see there's a sort of an oscillation that reflects the way that this variational approach works. But in fact, even if we're wrong, even if it isn't, the argon retentivity of feldspars is not dictated by relative size, even if it's dictated by different frequency factors, as in this case. As long as diffusion is the rate limiting transport step, you will recover an accurate thermal history. Okay, not to dwell on this, but if feldspars do contain these diffusion domains, what are they? We have a bunch of insights we can make. The first is that they have to vary by about 2 or 3 orders of magnitude, and we know this because, in fact, when we make models like this, our most retentive domain is about 6 orders of magnitude in diffusivity lower than the least retentive domain. Okay, so 6 orders of magnitude in R squared, 3 orders of magnitude in R. So whatever the biggest domain is, the smallest one can't be more than about 1,000 times smaller. When we crush these feldspars in this fashion I mentioned to you earlier, and we've done this for a variety of minerals now, what we find is, and here's a R&R knot plot, here's the uncrushed material, the original sample shown in yellow here. We reduce the size of the feldspar aggregate from 0.5 millimeter to 138 microns, and we in fact don't change the Arrhenius behavior. We have not reduced the retentivity of argon in that sample. We reduce it down to 54 microns. We're getting the gas out of the sample much more easily. In fact, at 54 microns, I can completely degas a feldspar at 1100 degrees. I can't do that with a sample that's 0.5 millimeter scale. By the time you get down to 42, we've really substantially reduced the retentivity. So from this, we infer that the largest domain is order, okay, that should be microns, and the smallest then between, 3 orders of magnitude smaller, between about 1/10 and 1 micron. Typical basement K feldspar, as I've mentioned, it's a mix. Here's an electron TEM image. There's 500 nanometers showing this tweed structure. This is essentially relatively small variations in in triclinicity in this material. If, in fact, at this scale, if there were a substantial number of line dislocations, you, in fact, would be picking it up in a region like this. So this is essentially, homogeneous, almost pure orthoclase, varying between, just small degrees of difference in triclinicity. This is Ian Parsons. Ian, one of our more fierce critics over the years, the guy who actually inspired the heterogeneous diffusion model, because the view is sort of we don't really see the Tweed feldspar here, but these are the microstructures that develop in a granitoid feldspar as you cool from high temperature. One is the creation of so-called modified feldspar, basically distillation, reprecipitation. And eventually, at low temperature, when you hit the solvus, and I know all you guys know what that is, you're going to, in fact, in the regions that have any appreciable sodium in, you're going to exsolve out albite perthite lamella. Okay? And what's fascinating, actually, is when these lamella form, at the very smallest scale, there's essentially just the difference between the unit cell of a potassium feldspar and an albite, an orthoclase and an albite. Say the orthoclase unit cell looks like this, and the albite unit cell looks like this. Well, that's an exaggeration, but something's got to give. At some point, you can just elastically deform that, but at some point, in fact, you actually break and you make a misfit dislocation, and that's what these little dots are. There, you do that actually in 2 dimensions. It's fantastic. It's like a series. It's like a chain link fence of tubes running adjacent to each of these little albite lamella. And this, we argue, because in fact these things are occurring at the tenth of a micron. These albite lamella in the Tweed feldspar, they're creating a diffusion distance on the order of a few tenths of a micron. Well, that's about 1,000 times smaller than 100 or 200 microns, the biggest domain, and that sort of works for us. You can, in fact, decorate these things in HF vapor, and you'll see as you get to very small scales, they disappear. So here, this albite lamella, we don't see the misfit dislocations because it's thin enough that basically it's, the strain is accommodated across that lamella. Here, these dislocations. And we believe, with I think good cause, that the smallest domains are in fact these regions of potassium feldspar that are bounded by these porous regions. Not continuously incoherent boundaries, but basically these little tubes, in fact, are essentially a short circuit to the Earth's atmosphere. 1% of what you're breathing is argon-40. This isn't an accident. Argon doesn't want to be down there. It wants to degas out of silicates and come up here. And actually, only to make the point that although when you heat these things up, these things exist. Now imagine you're exsolving the feldspar, you're making the alkalis are diffusing, and these lamella start to form, and the misfit dislocations at some point cut in the strain. They just can't stand supporting that strain, and they form. Now you'd think we put this sample in the lab, we heat it up at around 400 degrees, the alkalis are starting to move, they'd cut out. Actually, the opposite is true. In fact, our buddy Ian, in fact, demonstrated you can take these things up to 600, up to 1,000 degrees, and they never go away. And that's because actually material has been removed from those. Once you've made those misfit dislocations, small amounts of mass have been in fact removed, and preventing the reversed process from occurring. Okay, and this was my attempt to cartoon over here. Here's the K feldspar, and here's the albite, and I say because of the difference in the unit cell, eventually we're going to create a misfit dislocation. And we think that this is what provides the permeability to make these things so unretentive, and then to be preserved while we cook them up in the lab. Okay, just a brief example. I'm going to come back to this on Thursday. Despite the fact that the Indo-Asian collision is the textbook example of compressional origin, as you look from a satellite, actually the thing that really pokes you in the eye are these roughly north-south oriented rifts indicating east-west extension. And the bottom line is sort of, you're bulldozing the Himalaya up. Here's the sort of snow-crested Himalaya, Tibetan Plateau. This is the Indus Sangbo Suture right through here, the feature there. Now, these cross-cutting rifts are fascinating. I'm standing now here, looking almost due north at this range here, the Ninsing Tengla Shan. A bunch of very deeply incised glacial valleys going up. You can see the fabric, right? We're standing on the rift floor. You can see the master fault right there. So what we're going to do is we're going to walk up these incised valleys. We're going to collect below the master fault. We're going to collect in the undeformed granitoids going up and see if, in fact, we can realize that cartoon I showed you earlier. Okay, so the idea is this. It's deep, it's hot in the deep crust, it's cold near the surface. We have our sample down here that's going to find itself in the footwall of that normal fault. So it's at high temperature initially. There's slip on the fault. What's going to happen? Well, the hanging wall is going to bring cold material down, and it's going to refrigerate the sample in the footwall, depending on the slip rate. And eventually we're going to recover the sample. What does this mean in terms of slip rate? Well, we can translate this through a physical model of heat flow into a slip rate. So we've determined when the fault began to slip, okay, the peak rate, which corresponds to the slope of the cooling curve, when it truncated. Okay, so we've been able to do Paleo Seismology. In this case, as I'll show you, an event that occurred or began about 8 million years ago. We've got some constraint on it. Here's the geological map. Here's the rift, the Yongbajing Graben. Wang Ping knows this well. We're looking. Here's the trace of the master fault. It's dipping like so. We're going to go up in these valleys, map the geology, and then sample under the fault. This is, in fact, a valley up here. We're looking to the southeast. This is my daughter. She, on a Tibetan pony, came up and sampled this transect with us. Here are the results. We look at K feldspars from the valley bottom, okay, from the middle, from the top, and I'll just show you the top and the bottom. We translate, you see, from the valley top, we've got relatively old ages preserved, greater than 15 million years at the valley bottom. The sample came from hotter, deeper. Here's the thermal history that was recovered from the top. Here's the thermal history from the bottom. And here's the results from a numerical thermal model of movement on a 60-degree dipping normal fault in which slip rifting initiated 8 million years ago. And you can see the good agreement, relatively good agreement, with a slip rate of 3 millimeters per year. So from this thermochronology, we've determined, estimated when this fault started slipping, the slip rate, and in fact, this fault is still active. There's, high degree, there's 60-degree fault. Actually, relatively recently, Wang Ping, you'd know this. When was the last big earthquake here? Normal fault, 1937 or something like that. Okay, well, this, in fact, is telling us something about when Tibet bobbed up. More about this on Thursday. But, what's Tibet doing falling apart sideways? Well, again, it's you imagine a snow shovel here, right? And I'm making the Himalaya in front of me. Your expectation in your sand pile is that as you keep pushing, the sand will not grow infinitely high. At some point, it will exceed its cohesion. It will begin to fall apart. And in this case, the path of least resistance, in fact, is to escape out towards the Pacific Rim. Okay, now we're going to move into some more contemporary discussion of potassium, calcium, argon, Muscovite dating. The reason why K. Feldspar was the kind of proving ground of the multi-domain model is because it met all our criteria. It's an anhydrous phase. It was happy in the vacuum, right? Doesn't care whether we take it down to 10 to the minus 9 torr or not. But hydrous phases, biotite, for example, you put biotite in a vacuum extraction furnace and you even just warm it slightly and it starts to blow up, right? It's unstable. It'll dehydroxylate, dehydrate. And we kind of assumed the same was true for muscovite, although for years, for decades, there's been hints. The fact that the muscovite yields age spectra that look a lot like what you'd expect from a multi-domain model was tantalizing. So, been long used, though. Imagine, muscovite. It's certainly the most common datable mineral in low-grade regionally metamorphosed terrains, present in S-type granites. High potassium, 10% potassium, doesn't like excess argon. Okay, biotite actually, not in addition to this big range in closure temperature, it'll suck up excess argon, frankly, as soon as you look at it.
Mark,
yep.
Can you remind us what an S-type granite is?
Oh, a perluminous granite. I think this came up the other day when Sue was talking about Sue here. Sue, what? Yeah, what was the context? Perluminous. S-type is, in effect, an implied sedimentary source, a metapolitic source. So, this would be a granite that would be characterized by muscovite, K. feldspar, monazite quartz, as opposed to sort of a Cordilleran type, I-type igneous source, which would be hornblende biotite, plagioclase, and so on.
Why the old Plano-Aiken breaks would be perluminous granite if they weren't.
And Macusani is perluminous. Yeah. Okay, so actually, muscovite is a bit of a rascal because it actually is more retentive of argon, seemingly than biotite in nature. But remember, I said ideal diffusion experiment. We put the K feldspar in the vacuum. It's happy up to 1100 degrees, and then we melt it. This guy here breaks down at relatively low temperature. If you don't cook a muscovite up in the lab to 600 degrees, you're not going to see any argon movement. You take it above 700 degrees at a couple of kilobars, and it's going to turn into sanidine plus quartz. Okay, so this is a rascal. So we basically, for years, we're living with a closure temperature of 350 plus or minus 50 degrees. And it sort of worked because we knew it was more retentive than biotite, which we had this nominal closure temperature, but it didn't really. Anyway, we made some progress recently, and that is we devised a way to take the experiment, instead of doing sort of 2-3 kilobars, take the material up to 10 kilobars, 20 kilobars, and we actually then can stabilize to muscovite to higher temperature and get some argon moving. The surprising thing was when we got the samples, we radiated and recovered it, it produced, and this is normalized, so this is sort of the original age. In this case, it was a mica that's 325 million years old. And you can see that we degassed it in modern time, but it shouldn't behave this well. This is the apparent age spectra, normalized to 4039 for these various. Every sample did this. And, the ones that were degassed more, had lower peak ages. This is diffusion behavior. And somehow we took this hydrous phase, kept it stable in the piston cylinder at 20 kilobars, say, but then put it in a vacuum at 10 to the minus 9 torr, and the argon was released as if the material was stable. It's a hydrous phase. Muscovite is kind of interesting. It actually breaks into, sort of dehydroxylates, but it produces a stable dehydroxylate form that, in fact, remains, or at least retains the relative spatial position of the daughter product up till high temperature, above 1,000 degrees. So from this, we can calculate diffusion coefficients. So here's our Arrhenius relationship for 10 kilobars from these piston cylinder experiments. Okay, so we now have an activation energy. And you can see there's an activation volume. Sir Greg also showed you that when pressure is, now that we're going up to 20 kilobars, we have to account for the fact that there's an approximately 15 cubic centimeter per mole activation volume for argon in micas. So, roughly about an order of magnitude lower diffusion coefficient per 10 kilobars. Okay, but the typical muscovite in the crust is going to have argon closure at about 5 kilobars. So we're in fact going to need to use that activation volume to scale the Arrhenius relationship to where muscovite would typically. In a muscovite, of course, is a very common mineral in accretionary terrains. So if your muscovite has been down to 30 kilobars or something, or 30 kilometers or 35 kilometers depth at low temperature and is only closing, is closing at high pressure, then that calibration is probably right for you. In addition, there's a datum from the literature going back a little ways that we like because it was an unpublished master's thesis from Brown University 30 years ago that has been, frankly, unnatural acts have been performed on this in order to get the 350 plus or minus 50 degree closure temperature. But the bottom line is it's just wrong. Okay, it should have remained unpublished. So we have a Arrhenius relationship. Same thing I showed you earlier. The sizing experiments. Despite the fact that we're putting a hydrous phase into the vacuum, it behaves really a lot like the K feldspar I showed you. That the coarse material, is highly retentive, and as you reduce the domain size down into the tens of microns, it becomes substantially less retentive. So that's good. That means that we also know something that at least for this particular material, that the effective diffusion radius is order sort of hundreds of microns. This was extraordinary. This was an amazing result, which is, here's now, we're not normalized. Here's the actual age spectra from those experiments. We took a mica up to 730 degrees for 240 hours, 56 micron sample. We recovered it 10 kilobars. And here's the age spectrum shown in black. When we use our Arrhenius results, when we use the 63 kilocalorie activation energy, we predicted this age spectrum here. Okay, which looks like, in fact, it's predicting more or less. Then, the penny drops. Wait a minute. One experiment we're doing at 10 kilobars. The other one we're doing at 0 kilobars. When we, in fact, use that factor of 10 difference, by God, look at the fit. It's extraordinary. So, this is new. We really heretofore didn't know that we could take this very common mineral, muscovite, and treat it in this way in order to get the potential for continuous thermal histories is there. Here's another sample from the experimentally treated stuff. Here's the age spectra shown in gray. Shown in what have I done? No, the measured is shown in red. I'm sorry, and I've got two samples on here. That's why. Okay, and the MDD model shown in gray. So yeah, sorry, no, I've mixed up the colors here. The only point is it fits well to the multi-domain model. Here's the R0 plot. But if we'd known this going in, we could have saved ourselves a lot of fussing with high-pressure experiments, because it turns out that the big domain, okay, where most of the gas is, and this is where we're going to get our diffusion information from, when we plot the argon-39 diffusion coefficients, guess what that gives me? 63 kilocalories per mole. We didn't have to do the piston cylinder experiments. We could have just paid attention, looked at the samples. This, of course, is the small domain stuff. That's the reason why you don't get convex upwards age spectra. This is basically the small domain degassing, the big guys. So the potential there is fantastic, and this really remains unexploited. Just quickly, we also did, with Matt Heisler, one of these age elevation studies, and the bottom line is here's a lot of data all the way down this mountain in New Mexico, and these are very old samples. And you can see here's the sample at the high elevation, the low elevation. We can get continuous thermal histories from the Muscovite, and that's in fact telling us that there was a 20 kilometer per degree geotherm between about 1200 and 800 million years. This is information that we really haven't had before. Okay? The ability to actually look at paleogeotherms from vertical traverses. Do it with K feldspars. Now we can do it with Muscovite. For 100 micron, 150 micron radius cooling at 10 degrees per million years is 450 degrees. So, really not even in the range that was classically used.
Do you have a comparison of the Muscovite and K-spar in the same sample?
No. There's not yet. Okay, now for something a little different. We mentioned that the potassium-calcium dating hasn't really been utilized in the past because, say any radiogenic calcium-40 is lost in this sea of common calcium-40 we live in. But some recent developments, and I mention this too because I think there's real promise here, and also it's really cool. Okay, now let's abandon argon 4039 because calcium is condensable. 4039 is limited by the fact that I'm not actually directly going in. I'm not taking some kind of microprobe and looking at the distribution of. I'm creating a model, okay, and then I'm taking this degassed argon 39 and I'm putting it sort of into a crucible, which is called the multi-domain model, and I'm going to extract kinetic information. And as I showed you from that diffusion compensation plot earlier, I don't do a really great job of recovering the correct, or the canonical activation energy. It doesn't matter because of the diffusion compensation, but it's nonetheless a bit of a concern. What if we could actually go in, and I don't have to make up a story about domains, what if we could actually go in at a very fine spatial scale and measure these ages? Or even better, what if I were to take a picture of that and see what the age distribution is? It, in fact, do I see radial gradients or what? So here's the promise of this approach here. So potassium 40, 90% of the decays go to calcium 40. Here's an ion microprobe. You guys may not be familiar with this. This is our 1270 at UCLA. Essentially, it's a big mass spectrometer, the front of which, right here, is a variety of ion beams. We can put a 1 micron O- beam on your sample. We can put a half a micron cesium beam or half a micron gallium beam, depending on what it is you want to ionize. And actually, at a very small spatial scale, right, at sort of the spatial scale of argon 39 recoil, reveal age data, except you can't ionize rare gases, okay? Just, you can't, okay? So we can ionize calcium. So what we did is we thought, maybe let's have a look. Our mass spectrometer can go up to a mass resolution of close to 10,000 and not lose any sensitivity. Those of you familiar with these things, I can make it get higher mass resolution. What do I mean by mass resolution of 10,000? I'm going to be able to see a molecule of a mass of 10,000 from a molecule of a mass 10,001. Okay, and the problem is, calcium 40 and potassium 40 require a mass resolution of about 25,000 to separate. That would be a mass spectrometer that would roughly stretch from that window to the opposite wall. We don't have one of those. Okay, we've got the 1270. You can start to, if we really tighten the slits down. We, in fact, here's a very old Muscovite. Here's a 2.95 billion year old Muscovite. There's the K40 peak, okay, the mass to charge, and here's the calcium. So, we're almost there, and it's tantalizing. But when we actually try to use this to date, it's, we don't have flat top peaks. It's a mess. But wait a minute. Once you've made potassium plus, okay, you've got an alkaline metal. it really has a rare gas electronic structure, right? It's got to be really hard to make potassium plus plus. Like it's got to be really hard to ionize argon. So it occurred to us that if we were to, in fact, look at the double plus species for both potassium and calcium, we could potentially really suppress potassium. And in fact, you know what? we can suppress it by a factor of 1,000. It's extraordinary. This is a mass resolution spectrum, about the same 15,000 or something like that. Just to show you that the calcium 42 and calcium 44, we're seeing a little bit in this. Notice that the mass over charge, instead of us being up around 40, we're now at about 20, right? Because it's mass over 2 plus. Okay, so here's calcium 40, and you can't see potassium 40 next to it. Okay, it's disappeared. We've suppressed it so much. On the other hand, I told you earlier, potassium 39 is 10,000 times more abundant than potassium 40, and it's in a constant isotope ratio with potassium 40. So, although I have suppressed potassium 39 by a factor of 1,000, there's still lots of it around. So I can simply take that peak, multiply it by 1/10,000th, and I have the parent. So the parent-daughter relationship, like in the 4039, is essentially the daughter over this proxy, potassium 39. And actually, this works out great. The stability of our ability to in fact make that measurement and then correct for any common calcium, right? Remember, we live in this ocean of calcium 40, 1.5% of the planet is. Well, I simply need to measure calcium 42 or 44, multiply by the ratio, the common calcium ratio of 40 to 44, 42, and I get my radiogenic component. So this has been highly successful, and I'm going to just show you one example, kind of as the final scientific. This is that 2.95 or 3 billion year old Argon aged Muscovite. It's from the Pilbara. You guys recognize this maybe from classic Landsat images. This granite greenstone belt in the northwestern Australia. Our sample comes from an amphibolite schist right here. Got cooked up a little bit by the emplacement of these Archean granites. This is a scale of 100 microns. I've used a fairly coarse, this is early days, but the potential is for us to get down to, essentially a few microns in length scale. And you can see, well, maybe you can't, age variations. Let's look at this guy here. We plastered this thing with data. Ages get as young as 320 million years, as old as 3.1 or 3.2 billion years elsewhere. So we're sustaining extraordinary age gradients over, tens of microns or hundreds of microns length scale. Why do the ages get so young down here? This region is chock-a-block with small-scale cracks and features. The effective diffusion radius is small here, and it's relative. So I've just arbitrarily chosen this region here. Ages go from 3.1 billion down to I can't even read it. 2 billion years or so. I could have taken any other arbitrary region, but this is nice in the sense that I can plot a parent age versus distance from the oldest age in that profile. These are the individual data, sort of at a scale of tens of microns, and we have preliminary information about the diffusion of calcium in Muscovite, and this red curve here produces this thermal history shown here. The blue curve, so although I'm not fitting this perfectly, just to point out that the blue curve, which is substantially younger, about 100 million years younger, shows an indistinguishable thermal history. So again, the thermal sensitivity of the method is demonstrated here. This isn't the prettiest example, but what you're seeing is absolutely sort of hot off the press data. And so now this opens up the possibility of us, instead of inferring diffusion distributions from degassing and running our data through a phenomenological model of actually going in and at the micro scale being able to date this. In addition, this approach of actually doing spot analysis is inferior to what we eventually want to do, which is to do direct ion imaging. That is, this is not just an ion microprobe in that we date spots, it's an ion microscope. We, in fact, can determine the age distribution in real time, either by directly transmitting ions from the surface in optical continuity into the collector, or by high scale, by rapid rastering of a micron scale beam. So, in fact, instead of me having to connect the dots and make contours, we'll be able to get a direct picture of a 20 by 20 or a 30 by 30 micron region.
Mark, when you have a distribution of age, would you actually call the actual age of that larger sample just the oldest that you've observed?
I'm not sure I understand the question.
It's
only that when did that crystal? What is the rock forming age of that? It's at least 3 billion years, 3.2 billion years.
So you kind of go by the oldest measure.
No, the oldest wins, but it's not but that's a lower bound on what the age of formation of that crystal is. Yeah. Thermochronology isn't good about telling you about rock forming ages. It wants to tell you about the temperature history subsequent to that.
You can use the ion imaging technique on zircons too.
We do. We actually
Already have.
we have in terms of you guys might know about the titanium and zircon thermometer. Okay, so we actually developed ion imaging specifically to look at pictures of titanium to recognize that, for example, my Hadean zircons contain substantial contamination along cracks, and this was very helpful in us being able to winnow out or to find contaminated samples. Spot analysis, we couldn't tell. But seeing the picture emerge of the spatial relationship of a crack, and actually seeing the contours directly spatially related to the crack. That's so that.
What's the spatial resolution of the ion imaging?
It's the length scale. It's a spatial scale of the probe you use. So we can get a probe spot down to a fraction of a micron, but there'd be so little signal it wouldn't be worth it. So at the micron scale for old samples like this, you want to run this overnight, should work. So yeah, how quickly do you want your answer, and how strong is the radiogenic signal? Because you can get to a probe size where you could basically just produce noise. So that's the trade-off. Okay, well I'm wrapping. Yep.
What's the youngest history you can get today?
We're dating Paleozoic Muscovites. This approach seems to work, but not with the 1 micron beams. But this is early days. For those of you that know a bit about this, you might have already gone, oh, wait a minute. If you can do potassium calcium dating, why can't you do rubidium strontium dating? There's an alkaline metal and an alkaline earth. The problem there is that you need a mass resolution of 300,000 to separate rubidium 87 from strontium 87. That's a mass spectrometer roughly the size of Oakland, okay? And we don't have one of those either. But no, because actually the same thing happens. The rubidium gets completely suppressed. It's a little more complicated because we don't have a fellow isotope that's 10,000 times more abundant in the rubidium system, but we've actually figured out a way to go at this. And actually that's, in terms of ultimate spatial resolution, I think that's as or more promising. Okay, just wanted to finish up. I think I got a minute or two, do I? Yeah. Just to drive home, this occurred to me last night thinking about the overarching message, which is caveat emptor. Okay, thermochronology. If I was somebody just emerging in graduate school and thinking about this is a fabulous field because there's really important fundamental work to be done. I say largely in developing the kinetic calibrations that sort of The previous generation just got lazy and said, the closure temperature of. There is no the closure temperature. I could leave you with one take-home message: is biotite does not have. It's not a material constant. It is a variable dependent on a whole bunch of things, and actually, because it's much more interesting and much more ultimately powerful. But not until we get all the calibrations in place. I was at a meeting, a thermochronology meeting in Glasgow last August, and Pete Zeitler got up and gave a really odd talk, and it just to sort of drive home that it isn't just me. That I think Peter feels that we're now sort of at a stage where we're spending too much of our time gaming. That we generate some data and then we put it into P-cube or some other dynamic model, and it spits out multicolored diagrams that look good. But the fundamental assumptions underlying those pretty color diagrams are flawed. So he presented this: how clean is our laundry, and began with this takeoff on the poster of how green was my valley, and arguing that the state, that we now have international meetings. The state of thermochronology is strong, but asking how strong is the state. And for much of the same reasons I've mentioned today. Peter's take is that our inability to really either become adults or get out of our midlife crisis, whichever it is because of the interplay between three groups. There's the thermochronologists, which Peter characterized as the spandex-clad cyclists, the geologist, and the mineralogists. And I mentioned earlier that our fiercest critic has been famous feldspar mineralogist Ian Parsons, and that's because, in fact, the thermochronologist sees this as he's got this phenomenological model in mind, and this is how it works. The geologist, the guy who comes to the lab and wants a bit, he really doesn't care. He wants the closure temperature to be 300 plus or minus 50 degrees. And the mineralogist is like, if you people only knew how complicated these materials are, you'd give up. So this is the last slide, and that is that Peter sort of feels that the community has to basically decide between the extremes. That he feels that effort is being expended at the two ends. H, of course, the Hirsch index, right? The high, the guy that sort of yeah, that's right, or sort of got there first. Is that's one end member. The other is that people coming into your lab, it's they think the closure temperature of biotite's 300 plus or minus 50 degrees. Let them think that, because they're check cashed, and that's how we're going to keep this operation. And that there really is insufficient activity here. And this is sort of if you can see it, a bring out your dead, I think, slide from Monty Python. So this is, I don't know why Peter thought that was clever problem solving, but I'll leave it there. Thanks.
Quick question.
Given the development in the basic methodology and all that, so when we read old literature, how much of it can we believe?
Well, caveat emptor is about all I'd say that you can find the answer you want in the literature, but keep these remarks in mind as to whether or not they're based on an agreed convention amongst a community, or reference to a real objective observation.
Recast my question: how much reworking needs to be done for, say, solving the problems?
A lot of the problems we have, and I was stunned yesterday listening to Anna's talk and Sue's talk, the degree of frankly, well, not unanimity, but it looks like there's a group moving towards an identifiable direction. Wang-Ping, you know that for every 4 Himalayan Tibetan geologists, there are 5 N-member tectonic models, right? And that, in fact, I'm going to show you a slide of this, that essentially as time goes by, as the data is exploding, the number of models is increasing, not converging. And part of it, a small part of it, you can blame on the fact that a mica age from southern Tibet or the Himalaya has been used in the literature in seemingly sensible journals like Science and Nature as evidence for the time that the plateau was raised, the time the plateau started falling apart, the onset of convergence. So the elasticity of the thermochronological data is part of the problem in the Himalayan Tibetan community not being able to see collective way forward.